Mechanical pigs scrape away deposits to restore efficiency. This ensures optimal productions.
Welcome to this video on Module 6, Inorganic Scales and Sand Management. In this video, we will explore the importance of preserving flow geometry and asset integrity in oil and gas operations. It is prepared by Dr. Qureshi from the National University of Singapore, who specializes in the area of flow assurance. We begin with Part 1, focusing on inorganic scaling. We will examine the critical aspects of brine chemistry and how mineral precipitation affects your assets. Scale involves the deposition of hard, inorganic minerals from produced brine. Unlike organic deposits, these are crystalline, rock-like structures that bond to metal, reducing internal diameters and throttling production. Why does scale form? It is primarily driven by pressure and temperature changes, which can cause CO2 exsolution, and water incompatibility, where mixing incompatible waters, like injected seawater and formation brine, leads to rapid mineral precipitation. Water incompatibility is a major concern. When seawater containing sulfate ions mixes with formation brine rich in barium or strontium cations, it creates highly insoluble barium sulfate, a devastating and permanent scale. This table highlights common oilfield scales, their chemical formulas, the primary triggers for their formation, and their specific solubility characteristics in common treatments. Scaling tendency is often measured by the saturation ratio. When this ratio exceeds 1, the solution is supersaturated and precipitation is likely. We also must consider inverse solubility, where some minerals become less soluble at higher temperatures. Crystallization occurs in two main steps: nucleation, the initial formation of microscopic crystal seeds, followed by crystal growth. Inhibitor chemicals are designed to interfere with these specific stages. The cost of inaction can be catastrophic. Severe scaling has the potential to block tubing or flow lines entirely within weeks, leading to significant lost production, expensive workovers, or even total well abandonment. Several locations in your facility are particularly vulnerable, including the near wellbore formation, gas lift valves and chokes, subsea trees and manifolds, and heater treaters where temperature changes are common. Deposition within the tubing string acts as an ever-tightening choke. This reduces cross-sectional flow area, increases frictional pressure drops, accelerates production decline, and can even create critical safety hazards by interfering with downhole safety valves. We manage these risks using specific chemicals. Threshold inhibitors adsorb onto active growth sites to block crystal development, while nucleation inhibitors increase the energy barrier required for initial crystal seeds to form. A widely used technique is the scale squeeze operation. Here, chemical inhibitors are pumped directly into the reservoir rock, where they adsorb and slowly desorb over time, providing continuous protection for the produced fluids. Various remediation strategies exist, ranging from chemical treatments like acid washes or chelating agents to mechanical milling, and the use of specialized topside equipment like sulfate removal units to prevent scaling before it begins. Finally, we reach Part 2, Sand Management. In this section, we will discuss the challenges associated with erosion, sand transport, and the importance of effective separation techniques. Moving to the sand problem. Sand is produced when fluid flow stress exceeds the cohesive strength of the reservoir rock. This results in two major threats: erosion of high-velocity components like valves, and deposition in low-velocity sections, which can cause blockages. Erosion is a mechanical wear process driven by kinetic energy. It is highly dependent on fluid velocity, increasing exponentially. Impingement angles, such as those found in tight elbows or blind T's, are particularly vulnerable, especially in high-rate gas wells. APIRP 14E provides a traditional empirical standard to calculate maximum allowable velocity to avoid erosion. However, it is conservative. Modern approaches now prefer computational fluid dynamics to accurately model particle trajectories and localized wear. Understanding sand transport mechanics is vital. In horizontal pipelines, a minimum fluid velocity is needed to keep sand suspended or moving as a bed. Terrain effects, like pipeline dips, also cause sand accumulation, leading to flow reduction and slugging. Effective production management requires balancing within a specific window. We must maintain high enough velocities to prevent deposition, while staying low enough to avoid catastrophic metal loss due to erosion. Real-time monitoring helps us stay within safe limits. Acoustic sand detectors, or ASDs, identify the signature sound of particles hitting pipe walls, while insertable erosion probes provide direct measurements of physical metal loss over time. Prevention starts downhole. Controlling sand production at the source remains the most effective strategy for managing these risks before they enter the production system. If sand reaches surface facilities, it must be removed. Descenders, or hydrocyclones, use centrifugal force to separate sand from fluids, while separator jetting uses water jets to clear accumulated sand from the base of production vessels. We must also consider synergistic threats. Sand can act as nucleation sites for scale, while scale can cement sand into hard blockages. Furthermore, erosion strips away protective corrosion layers, exposing metal to aggressive corrosive fluids. Late-life field operations introduce unique challenges. Rising water cuts increase scaling ions and fluid velocity, while also raising chemical operating costs. Engineers must use dynamic modeling to simulate these conditions early in the design phase. Subsea delivery systems require careful material selection. Because scale inhibitors are often acidic and viscous, delivery tubes in subsea umbilicals frequently utilize corrosion-resistant alloys to ensure the system itself does not fail during injection. Managing scale and sand is a life cycle process. It starts with prediction through analysis and modeling, followed by preventative completion design, mitigation through injection and monitoring, and finally, remediation using washes or mechanical operations. A core flow assurance axiom reminds us that ignoring water chemistry can lead to permanent blockages from barium sulfate scale, effectively choking a well long before other thermal issues like wax or hydrates even develop. In summary, water mixing, targeted chemical delivery, and strict velocity windows are foundational to successful management. A holistic approach is essential, viewing all solid phase risks as an integrated system rather than isolated problems. That concludes our video on inorganic scales and sand management. Thank you for watching. Our next module will focus on corrosion and erosion in subsea infrastructure. If you are interested in discussing these topics further, I am available for consulting engagements, joint research, or professional training. Please feel free to reach out via the email addresses provided or connect with me through my professional network. Thank you again for joining this session.